Hello everyone. Today I am going to explain the topic of transport phenomena, which is equation of change for a cylinder rotating on its own axis. Here we are going to learn about its derivation and its related numericals. So, for this, the problem definition will be a liquid of constant density and viscosity is in a cylindrical container of radius r as shown in figure. The container is caused to rotate about its own axis at an angular velocity omega. Here, the cylindrical axis is vertical, so we can take gz is equal to minus g, which is the magnitude of the gravitational acceleration, and also gr and g naught will be is equal to 0. So for this problem, we are going to derive the equation for velocity profile, and we are going to find the shape of a free surface of the liquid when steady state has been established. So for this problem, we are going to take or use the continuity equations for cylindrical coordinates, which is 1 by r into d into r into vr by dr plus 1 by r into dv theta upon d theta plus dvz upon dz is equals to 0. Also, we are going to use Navier-Stokes equation, which is rho into dvr by dt minus v square theta by r is equals to minus dp by dr plus mu into del square into vr minus vr by r square minus 2 by r square into dv theta by d theta plus rho gr. This equation used to describe every possible motion for a Newtonian fluid. So, after this, we are going to take some assumptions for this problem. As the flow is in steady state, d by dt is equals to 0. As there is axial symmetry, therefore d by d theta is also is equals to 0. And there is no radial and axial flow, therefore Vr and Vz will be is equals to 0. No slip boundary condition will be applied, and the gravity will be only on z direction. Therefore, Gz will be is equals to minus g. Also, the viscosity and density of the fluid will be constant. So, by applying all these assumptions, we are going to simplify the Navier-Stokes equation, and from this we get three equations, which is mu into d by dr into 1 by r into dr v theta by dr is equals to 0, dp by dr is equals to minus v square theta by r, which is r component, and dp by dz is equals to minus rho g, which is z component equation. Therefore, by using theta component equation, mu uh, by using theta momentum equation, mu into d by dr into 1 by r into d into r v theta by dr is equals to 0 at boundary condition r is equals to capital R and v naught v theta is equals to omega r. By applying this boundary condition and integrating the theta component, we get v theta is equals to omega r, which confirms that linear velocity confirms rigid body rotation. The fluid no longer shears its spins as if it were a solid block of ice. After getting this v theta, the value of v theta, we put the value of v theta in the above equation of r component and z component. From this we get the r momentum equation, which is dp by dr is equals to rho omega square into r, which tells the centripetal acceleration drives a pressure gradient outward from the axis to the wall, and the z momentum equations dp by dz is equals to minus rho g, which says that gravity drives the standard hydrostatic pressure gradient downwards. Now, by getting these values, we we are going to put these values in the total differential equation from which is dp is equals to dp by dr into dr plus dp by dz into dz is equals to rho omega square r dr minus rho g dz. By integrating this, we are getting the pressure field, which is P, which is the function of r comma z, it i- is equal to 0.5 into rho omega square r square minus rho gz plus c naught. The pressure at any point inside the rotating fluid is a delicate exact balance between the outward centrifugal spin and the downward hydrostatic force. From this, we get the equation of the free surface paraboloid, which is Zs into r is equal to h plus omega square upon 2g into r square minus r square by 2. Here Zs tell us the geometric curve of the surface where p is equals to p atm and h is the height of the fluid, and omega square by 2g tells the fundamental curvature of the fluid. Now, the shape of the surface depends entirely on rotation, speed, and gravity. Fluid density and viscosity are completely mathematical, irrelevant to the final shape. We move on to the numericals. Here we are analyzing fluid flow between two coaxial cylinders. The inner cylinder has radius kr and the outer cylinder has radius r. Both cylinders are rotating but possibly at different angular velocities. Because the fluid is incompressible and the system is steady, the flow depends only on the radial position. Therefore, the velocity distribution develops due to rotation of both cylinders. The key idea is that fluid layers experience shear due to the difference in rotational speeds. This creates a velocity profile between the cylinders. Now, we consider two immiscible liquids rotating together in a beaker. Since both fluids rotate at the same angular velocity, therefore the interface between them takes a curve shape. So, from derivation from the above problem, which we choose to rewrite as v theta by r is equals to d1 by d2 into r by r whole square. By putting the boundary condition v theta kr is equals to omega I kr and v theta r is equals to omega naught r, we get omega I is equals to d1 plus d2 into 1 by k square and omega naught is equals to d1 plus d2. By simplifying this differential equation, we get the final expression, which is v theta by r is equals to omega naught by omega I k square upon 1 by k square plus omega I minus omega naught upon 1 minus k square into k r upon r whole square. So, after this, the next question will be: a glass filled with Newtonian fluid is rotated at n is equals to 10 rpm, where there are given some reference point on the axis, which is p, q, r, s, t, u in centimeter. In centimeter, we are going to find their z coordinates. So here we are analyze a rotating fluid inside a glass. First, we calculate the angular velocity using the relation omega is equals to 2 pi n by 60, which is equal to 1.0472 radian per second. Now, we using the paraboloid equation, ZSR is equal to Z naught plus omega square by 2g into r square, which gives us 0.05589 meter inverse. Now we compute the height at different radial positions from 1 centimeter to 5 centimeter. From the results, we observe that the height increases very slightly as we move outward. The values are extremely small in millimeter range. So the conclusion is that at low speeds like 10 rpm, the free surface appears almost flat. Also, an important observation is that the shape of the surface depends only on angular velocity and gravity. Now we are moving to the further num- further and last numerical, which is rotating cylinder completely filled with fluid. Now we consider a vertical cylinder completely filled with fluid and rotating at 20 rpm. Here we are going to determine velocity profile, pressure distribution and maximum fluid velocity. For velocity profile, since the container is fully filled, the fluid undergoes solid body rotation. This means every fluid particles rotates together and the velocity increases linearly with radius. So, velocity is 0 at the center and maximum at the wall. Therefore, for pressure distribution, the pressure inside the fluid varies due to two effects: centrifugal force in radial direction and gravity in vertical direction. From the equation, pressure increases with radius and decreases with height. So pressure is highest near the outer bottom region. Now, for maximum fluid velocity, the maximum velocity occurs at the wall of the cylinder. Using V is equals to omega into R, we calculate it to be 0.209 meter per second. So overall, this problem shows how rotation affects velocity and pressure distribution inside a completely filled system. Some of the key points we get from this is that the geometrical independence, that the physical shape of the rotating fluid is governed purely by kinetics and gravity. Fluid density and viscosity are ultimately irrelevant to the final geometry. Also, linear versus quadratic scaling. When fluid velocity scales linearly with the radius, the resulting internal pressure scales quadratically, which directly carves out the signature parabolic surface. And the third point is universal curvature. Whether carving the free surface for a single liquid or defining the hidden boundary between oil and water, the geometric rule of rotation remains absolute across all boundaries. Now that is all. Thank you.